All right, so we are graphing linear inequalities. So we'll start with the base here. I don't think there's too much algebra involved. Like we do have to change some stuff to y equals mx plus b, but just the basics here. The inequality, your four inequalities. This is less than, greater than, less than or equal to, greater than or equal to, and do whatever you need to help you remember those. But you don't even really have to know them because we're just graphing them. The algebra part of here that may run into possibly is everything works the same when you're solving. Like if you have an addition on the left side to get it to the other side, you got to subtract it over. If you subtract something on the left side, you got to subtract it on the right side too. The one different algebraic thing is this red over here. Is if you ever divide or technically multiply. In our case, it's always going to be divide though. But if you ever divide by a negative, you flip the sign, the inequality, you flip it. Okay, so we'll run into one of those problems in just a minute. You probably kind of remember that. I've heard that before, but anytime algebraically, if you are solving an inequality, if you ever divide by a negative, you flip the sign. Okay. The graphing part, this is where we'll mainly focus on today, is this part right here. Just kind of a refresher on some stuff right there. But we will still use like y equals mx plus b, okay? It'll just be like y is less than, or y is greater than, or y is less than or equal to, or greater than or equal to, or one of those, okay? But it'll all still work the same way, where m is your slope and b is your y-intercept. The first difference, so everything's the same besides these two things right here. The first difference is remember when we are solving a line, the solution is actually any point on the line, okay? So if it's just less than, that means it can't actually equal. Like it can't equal the line. It's just be everything less than the line. So if it's less than or greater than, you used a dashed line to signify that those points on the line are technically not part of the solution. So this is like the new thing. If it's less than or greater than, you use a dashed line. There is just a button right there on Alex that you will use to get that. We'll ignore the problem, but like this button right here, like if you go graph a line, you can just go click that line and change it to dashed or change it to solid. Okay, so we can just change that solid or dash. So if it's less than or greater than, it's dashed. If it's less than or equal to or greater than or equal to, it's solid. At the beginning of the problem, you can go ahead and write that down and find that. So we'll try to do that to remind us. The second part is a little bit more inclusive, but more stuff to do, but you have to shade. So since it is less than, like I said before, it's like all your solutions are anything less than that line. The easiest way to do it is if it is in y equals mx plus b, it's anything below that line is going to be shaded. But if it's hard to tell what's below and what's above, which sometimes it is, and we'll talk about that, the way you can do this to make sure, especially do this on a test, you can pick any point that's not on that line, and then plug it back into the original equation, and then if it's true, you shade towards that point. And if it's false, you shade away from that point. So we'll do that as we go through these, but those are the two differences. You got to look at dash or solid, and then you got to shade. All right, so the first thing we want to do here is just do a basic one here. This is y equals mx plus b. So here my slope is 2 over 3. So that is up 2 to the right 3. Good refresher over last week. And my y-intercept is 5. Okay. This is going to be a solid line because it is greater than or equal to. So that's our first difference. Well, let's go ahead and graph this. So we start at 5, 1, 2, 3, 4, 5. And then I do what my slope says. I go up 1, 2 to the right 3. And again, this is going to be a solid line because it's less than or equal to, or it's greater than or equal to. And that's my line. Okay. So now we have to do the shading part. Now, again, like I said, you might be able to look at this and say, okay, this is greater than, so I should shade above. So I'm guessing I'm going to shade on that side. But if you have a hard time seeing that, or just like double check your work when you're taking the test, to shade this, you want to pick any point that's not on the line. The easiest point, the one I'll pick all day if I can, is 0, 0. Because if I plug in 0, 0, it's easy to work with because 0 times anything is 0, right? So if I plug in a 0, 0, it can't be on the line though. So if my line goes through there, I've got to pick a different one. When I plug in a 0, I'm just going to plug in a 0 for my y. I plug in a 0 for my x. 0 2/3 goes away. So is 0 greater than or equal to 5? That is false. So what that means is that any point that I plug in down here would not hold true for this, okay? Since it's false, I'm going to shade away from that point. I am actually going to shade this side. And then what that means is any point that I plug in up here would hold true for this problem, okay? So I could plug in 0 10 way up here, and it would make that true when I plugged it in. I'll go back in just a second, but Alex has a paint bucket. Like you just drop the paint on one side or the other side. I guess it's not a bucket, actually. It's just a little circle there. But yeah, you just paint one side or the other side, and it shades it for you. So you just have to pick the right side, okay? And again, what that shading is signifying is technically any point that I'd plug in that shaded area would make this true. All right, next one. If it's not in y equals mx plus b, it's always easier just to put it in y equals mx plus b. Technically, you could graph your intercepts and do it that way if you wanted to. But I like to put it in y equals mx plus b, so I am going to subtract 2x from both sides. These cancel out, so I get negative 3y is less than negative 2x plus 6. And then to get y completely by itself, I divide both sides by negative 3. Here is that algebra point. I am dividing by negative 3. Anytime you divide by a negative, you have to flip the sign. Okay. So I'm going to, that's going to change from a less than to a greater than. So that's why I flip the sign. Negative 2 divided by negative 3 would be 2/3. 6 divided by negative 3 would be negative 2. All right. So to graph this, my slope is 2/3. So I'm going to go up 2 to the right 3. And my y-intercept is negative 2. I guess we'll go ahead and write this. This is just greater than, so this is going to be a dash line, right? So I start at negative 2, and then I do what my slope says. My slope says I go up 2 to the right 3. And now I graph my line. I'm going to make a dash line. Okay. So I'm doing dash because it's greater than. You always do a dash when it's greater than or less than. If it has the equal to, you do solid. Now I need to shade one way or another. Again, if you can choose 0 0, you got to pick a point not on the line. So I'm going to shade using 0 0. Plug a 0 in. I always think it's easier to plug it in. If it's like this, plug in 0 0 to the top. You can plug it in down there. It'd be the same thing. But it makes it easy to plug it into the top one because everything on this side goes to 0, right? Because 2 times 0 is 0, 3 times 0 is 0. So is 0 less than 6? That is true. And since that is true, that means I'm going to shade towards 0 0. So that means any point over here. Since 0 0 worked in that equation, any point on that side will work in the equation. Y'all with me a little bit? So it's the same exact thing. The two differences are if it's less than or greater than, you have to do a dash line, and then you have to do the shading thing. All right. Sorry. I feel like something disappeared on me here. Okay, the next one is moving into systems of linear inequalities. So with systems of equations, remember when it was an equal sign, the intersection, the point where they crossed was the one point that was on both the lines. So we were always trying to find the intersection of like where they cross, because that'd be the one answer that worked for both of them. So on this one, since you have shading, what you're actually looking for is the intersection of the shadings. So I'm going to shade this line, I'm going to shade this line, and see where what region overlaps there, and that would be any answer in that region would work for both of them, okay? So let's just go ahead and graph both of these. The top one, that's going to be dashed, right? Because that's just greater than. Here, my slope is -3, so that'd be like -3 over 1, so that would be down 3 to the right 1. And my y-intercept is 2. So I start at 2. And then I'm going to go down 1, 2, 3 to the right 1. I'm going to do a dashed line. But I still got to figure out how to shade, right? All right, so shading this one, again, I just use 0, 0. Like 0, 0, if you can, it's just make it so much easier. So 0 is greater than -3 times 0 plus 2 is 0. -3 times 0 goes away. Is 0 greater than 2? That is false. Now, instead of shading that side on your paper, you have pencil, so it's a little harder to tell. On my side, I can do it. But what I would do is I would just put a little mark on your paper or something to show, hey, I'm about to shade that side. Because when you get pencils, it makes it harder to do. On my side, I'm going to just show you real quick because I have different colors. But just put a little mark on that side and remember that you're shading like to the right side of that blue, okay? All right, let's shade the other one, or do the other one. So on this one, this is going to be solid because it's greater than or equal to. My slope is going to be 3, or 3 over 1, so that's positive, up 3 to the right 1. And my y-intercept is 5. So I start at 1, 2, 3, 4, 5. And then I do what my slope says. Up 3 to the right 1. 1, 2, 3 to the right 1. That would be there. We said it's a solid line. Start at 5, up 3 to the right 1, solid line. So now we got to figure out where to shade. Again, some of you can look at it and say this is greater than, so I'm going to shade above the line. Like, if that makes sense in your head. But I always think it's nice to go ahead and just plug in 0, 0. When they get a little more vertical, it's harder to tell what's above and what's below. But is 0 greater than or equal to 5? That's false as well. Okay, so I shade away from 0, 0, so I'm going to shade this side. Again, on your paper, you may just make a little mark like that, okay? So I'm going to shade here, and just so you all can see the answer, my answer is actually this one right here. I guess I have my different colors here. I can just keep making them purple. My answer is actually only this region right here, okay? It is where the where the shadings intersect, right? My only answer is this. On Alex, I will only put shading in this region right here, okay? Now what you do on your paper is you put a little mark to the right of this, you put a little mark to the left of this, so I need to be to the right of the red line and to the left of the, to the right of the blue line and to the left of the red line. So that means I got to be, this is the only area that's hold true, to the right of the blue line, to the left of the red line. That is why you put that little mark on your paper so that you can find whichever region. Because on Alex, like I said, you're not going to shade all of it on Alex. You're only going to shade this little part right here, okay? But I wanted to do it with the colors just to show you like what you're actually looking for is the intersection of the shading on those, okay? Once you figure out, like we're going to do these where we have like 5 on one graph in just a second. And you got to be to the right of this one, below that one, to the left of this one, and all this kind of different things. But once you kind of figure out one, like make your little mark and just kind of puzzle it out to get there. All right. One thing that we did not talk too much about in week 1 that we don't have to talk to them about. I think y'all can use common sense to solve these, but just so y'all see it. Anytime you have x equals a number, it creates a vertical line, okay? So like if I had x equals 5, that's just a vertical line at 5. We need this a little bit for this, but like I said, I think you can reason through it. On this horizontal one, if it's y equals a number, it creates a horizontal line. So if I have y equals -2, I can just draw a horizontal line at -2. Okay. That may help you a little bit on these, but like I said, you can probably reason through this and get these answers. So we'll see this a little bit. And one of the things that happen is they start talking about manufacturing or exercise or whatever on these. I'll say it in just a second, but you can't have negatives, right? You can't exercise a negative amount of minutes. You can't manufacture a negative. So we'll see x is greater than or equal to 0 a lot because it can be 0 or more. It just can't be negative. All right. So what happens if we got to do 3 of these? So we can start with that x is greater than or equal to 6. The way that y'all know the x numbers are right here, right? So I know that all the x numbers have to be greater than or equal to 6. So it has to be something greater than or equal to 6. So what I'm going to do here is if you forget whether it's horizontal or vertical, if you put a dot right here, it doesn't really make sense to do it this way. So you're going to do it vertical. It's going to go vertical. It is a solid line because it's greater than or equal to 6. Okay. So that is solid. And we would want to shade greater than or equal to would be to the right side, right? So we want our number has to be greater than or equal to 6. Maybe I don't know, have to manufacture 6 things to make a profit or something. So we need to make at least 6 things, and then we have to follow the machines over the next formulas. When we get into actual examples, it'll kind of make more sense. All right, the next one, it is greater than, so dashed or solid? Dashed. I don't know, they may use the word like dotted or dashed, but dashed for this one because it's just greater than. My slope is -2, which is -2 over 1. That would be down 2 to the right 1. And my y-intercept is 5. So I start at 5, and then I'm going to go down 2 to the right 1. And we said dashed. A little easier on the computer to do dash than it is. I guess we might as well shade that one too, right? So shading it, it's greater than, so I'm guessing we're going to shade over here. But let's go ahead and check by plugging in 0, 0. Again, 0, 0 is always easy one to plug in. 0 is greater than -2 times 0 plus 5. Is 0 greater than 5? That is false. I think we get a lot of falses today. So I shade away from 0, 0. So I'm going to shade on this side. Again, I'm just going to put a little arrow there to signify that I need to be to the right of the black line, to the right of the red line. So right now my answer would be like right here, right? Not this area. But we got to do the next line. Here my slope is +2, so that would be 2 over 1. So that would be up 2 to the right 1. And my y-intercept is at -5. Oh, we didn't say this, but less than or equal to would be a solid line. So I start at -5. I'm going to do what my slope says. I'm going to go up 2 to the right 1. Solid line through there. All right, so again, you might be able to look at it and say less than or equal to. I'm going to shade below. Let's double check. I can plug in 0, 0 again because that's not on the line. So 0 is less than or equal to 2 times 0 minus 5. Is 0 less than or equal to -5? Nope. So I shade away from 0, 0. 0, 0 is on this side, so I shade the other side. So I want to shade this side. So I need to be below the blue line, to the right of the black line, and above the red line. I believe my answer would be right here, right? To the right of the blue, above the red, to the right of the black. And again, think about what we're doing here when you solve these. This means that any point in this area would satisfy all three of these equations, okay? So if I pick the point, 10, 0, or actually let's pick like point 10, 6. If I pick this point right here, 10, 6, and plugged it into this, it would hold true, this it would hold true, and this it would hold true. Okay, any point in that green area would hold true for those. All right, now we get into the fun ones. So to show how this is kind of used real life, this is a word problem. You have to come up with the equations. That's the hard part. Graphing them usually isn't terrible. The equations aren't terrible, I don't think, on this, but coming up with the equation is the hard part always. So Maria does a weekly exercise program consisting of cardio and weight training. Each week she exercises for at least 10 hours. She spends at most 8 hours weight training, at most 7 hours doing cardio. Let X denote cardio and Y weight training. Shade the region that corresponds to the X and Y that satisfy all these requirements. Okay, so what was it? It was X is cardio and Y is weight training. Other key side note here, and when you see at least, that's always greater than or equal to. When you see at most, that's less than or equal to. All right, first sentence, go back and read it. Each week she wants to exercise for at least 10 hours. So she wants to do cardio plus weight for at least 10 hours. So 10 hours or more. Next sentence, she spends at most 8 hours on weight training. So at most means 8 would be the maximum amount. Weight training is Y. So I'm going to have Y is less than or equal to 8. Next sentence, she spends at most 7 doing cardio. So cardio is X, at most 7. Now the one weird one here, I kind of already said this, but like almost all word problems this happens. Can't really exercise a negative amount, right? So I know that X has to be greater than or equal to 0 and Y has to be greater than or equal to 0. Those just like always happen. They don't really say that in the problem. That's just using common sense. No, okay, I can't exercise a negative amount. So I do want to put those on there as well. All right, we'll do the hard one first. This one right here. We need to get that in Y equals mx plus b. So I'm going to subtract x from both sides. So I have y is greater than or equal to negative x plus 10. So that is going to be a solid line. My slope, there's no number in front of x. That'd be negative 1, which is like negative 1 over 1. That would be down 1 to the right 1. And then my y-intercept is at 10. So I start at my y-intercept, which is 10, and then I go down 1 to the right 1. Solid line, right? Oh, wait, we got to figure out where to shade. So this is greater than or equal to, so I'm guessing I'm going to shade over here, but let's go ahead and work it out. Again, we can plug in 0, 0. It's always easier to plug in 0, 0 back at the original because it just makes it easier. So 0 plus 0 is greater than or equal to 10. 0 is greater than 10. That is false. So I need to shade up here. All right, the other line should be fairly easy. Y is less than or equal to 8. So again, if you forget if it's horizontal or vertical, go to y equals 8. It only kind of makes sense to go this way. Y has to be less than or equal to 8. So that's all the numbers down here. X has to be less than or equal to 7. So X always has to be something less than 7. So that's all the numbers this way. And then you have your X has to be greater than or equal to 0. So I'm going to draw the border here, and it's got to be something bigger than 0. And the same thing with the y. Y has to be greater than or equal to 0. So I'm going to do all the numbers over here. So you can kind of see, if I move this arrow over here just a little bit, I have to be in this box, right? But then I also have to be above the blue line. So my answer would be this region right here, okay? She can set her goals, or she will meet all those requirements, all her goals, as long as she picks some combo of cardio and weight training in here. So she could do 7 hours of cardio and 2 hours of weight training, or she could do 7 hours of cardio and 8 hours of weight training, or 8 hours of weight training and 2 hours of cardio. She could pick something in the green too. She could pick 6 hours of cardio, 7 hours of weight training, and she would meet all those. She'd work at least 10 hours. She wouldn't do any more than 8 hours of cardio or 7 hours of weight training. Any of those combinations would create that, okay? Starting to think of what the next problem was. Yeah, it is that. Okay. So the next, this is a little bit difficult because you got to come up with those formulas, and it will count it wrong if you do not put the x equals 0, or x is greater than or equals 0, and y greater than or equals 0, because you do need those, even though they don't really play into this at all. It might, like you might be looking for this section. The next part, so this is like all the different linear solutions. This is kind of the idea that people use this for. You can take several different constraints and put it all in one graph. But the next topic, the last topic for your test, is called linear programming. Linear programming does this right here, okay? There's just one thing that they do a little different, or one extra step. I'm going to make your life easy when I do this, so just hang with me for a second. So linear program would maybe say, these are all the possible options, right? She could work all those different hours. She could do 6 hours of cardio and 7 hours of weight or whatever. That's all the different possibilities. What linear programming does is it may write a function that they call the objective function, or the profit function. Here it would be objective because we're talking about calories. Profit if you were thinking about money, right? So the objective function for here would be like what would burn the most calories during a workout through the week, okay? And the way it works is you are going to look at the vertices here, like the three corners of this triangle, and you would plug it into that objective function and see which one is going to maximize her calorie output from these workouts, okay? So you could do this for like exercise or something like that. This one doesn't really have an example. That's why I talked about it real quick. But here is that same situation where we have these constraints. X has to be greater than or equal to 3. Y has to be greater than or equal to 3. Here, a formula that goes with it. And then it gives me what they call the objective function on this. And here we want to find the maximum value. So what would create the biggest output, okay? So maybe, you go back to exercise or whatever. Like you can say 3 hours, want to do at least 3 hours of cardio, at least 3 hours of weight training. This could be, who knows what that would be. But then that could be like, okay, they're burning 300 calories per hour with weight training, 800 calories per hour with cardio, like whatever. Like you could do, no telling what this could be. It could be all these sorts of different things. But what we're going to do to make life easier is we've already went through all these graphing things, right? And graphing this, and you're going to have to graph it whether you do this or not. But I am going to allow you, and if it's on the test, we'll figure it out next week, what's on the test and what isn't. But this Desmos.com is a free graphing calculator. You can graph these. Is it greater than or equal to 45? I feel like it was less than or equal to. It was less than or equal to. So to save you a little bit of time on these problems, instead of having to graph it and then look at it, and like you still have to learn how to use Desmos or look at it, because like here I had to zoom way in, okay? So it's kind of hard to tell with the reflection here, but the darkest part of this one is where all these intersections, or where all these shadings intersect, would be those three, that triangle right there, okay? That gives me like the three vertices that I need to solve the problem. So you're going to use Desmos to find where the shadings intersect, and then you're going to write down those 3 points. Okay. So that's my answer. That's my region. That triangle is the region that all these work. Oh man, I should have looked at that closer. I don't have it written down. 3, 9, 3, 3, 11, 3. Three, 3, 3, 9, 11, 3. Okay, so I take those vertices of the triangle and I'm going to plug them into this function right here to see which one would give me my maximum value. So 3 into x, 3 into y, 3 times 3 plus 8 times 3 would be 9 plus 24 is 33. 3 into x and 9 into y, that would be 9 plus 72 would be 81. This one, 3 into x, 11 into x, and 3 into y would be 33 plus 24 would be 57. So since we are looking for the maximum, the one that would generate the most is if my x was 3 and my y was 9. So I'm trying to make your life a little bit easier with this. You can plug it into Desmos, you can find those regions, look at those vertices, and then plug in those points to the objective function. But just be careful. This says maximum value. Sometimes you want the minimum value. If we're talking about the cost of manufacturing, we want to limit that down. So it will change that on Alex for you, or without telling you. So pay attention to that. So that one says maximum, that one says minimum. So again, graph those on Desmos, and then you can find the region that those intersect and plug those in to find that. And we're kind of doing one more in just a second. So, all right. So now we got to put like the last 2 problems we did together. Oh, I got those right there. I got your picture right there. Okay. Now, the last problem, I used to have this one on the test, but I guess I got nice. This one, you have to do your own linear programming on this one. So you have to come up with the equations, you have to graph it, you have to find the region, and then plug it in. Okay? The graphing is not hard because we're just going to use Desmos. Writing the equation is the hardest part. If you need to make a chart, make a chart. Honestly, I like the idea of making a chart. Let me read it real quick. A manufacturer produces 2 models of toy airplanes. It takes the manufacturers 20 minutes to assemble Model A and 10 minutes to package it. It takes the manufacturer 15 minutes to assemble Model B and 12 minutes to package it. In a given week, the total available time for assembling is 1,800, and the total available time for packaging is 1,080. Model A earns a profit of 12. Model B earns a profit of 8 for each unit sold. Assuming the manufacturer is able to sell as many models as it makes, how many units of each model should be produced to maximize the profit? Okay. So what I would do, and this is kind of the hardest part, I was trying to think of the easiest way to do it. It talks about assembling 3 times and packaging 3 times. And that is what I would try to identify. Let me use black. So my chart talks about assembling 3 times and packaging 3 times. And then you have Model A and Model B. Okay? And then I guess you have the total as well. So that's the 3 times it talks about it. If you can do that, then you can write the equation pretty easy. Because, let's just go ahead and fill out the chart. Model A assembly is 20 minutes. Model A packaging is 10 minutes. No. Model A packaging is 10 minutes, right? Model A packaging. Got to write that in the right spot. Model B assembly is 15 minutes. Model B packaging is 12 minutes. Everybody with me so far? And then the next sentence says the total available time for assembly is 1,800 minutes, and the total available time for packaging is 1,080. Okay? So my equations that I'm going to write, and this is where you can just say, okay, Model A can be X and Model B can be Y. would be 20x, so 20 minutes per Model A plane, and then 15 minutes per Model Y plane has to be I get total available time for assembly is 1,800. It doesn't mean I have to use all that 1,800. It could be less than or equal to 1,800. You're going to use an inequality on these because that's what we're looking at right now. And then for packaging, 10 minutes per package and then 12 minutes per package has to be less than 1080. Okay. To me, the hardest thing on these is to figure out what to make X and what to make Y. Because in my brain, I have two scenarios. I can make Model A be X and Y, or I can make assembly be X and Y. Okay. I know that it's not assembly and packaging because there are 3 numbers that talk about assembling. And I really only want 2 numbers to be an X and 2 numbers to be a Y. Does that make sense? That's the way my brain works. I don't know why. I'm just trying to make it easy for you. And they talk about assembling for Model A, they talk about assembling for Model B, and they talk about the total assembly time. So I'm not going to make that be my X. My X is going to be Model A, my Y is going to be Model B, and then I can do the assembly for A plus the assembly for B has to be less than or equal to total. The packaging for A, the packaging for B has to be less than or equal to the total amount of packaging. Okay. So if you want to make a chart like that, whatever is going to help you do that. Once you do 1 or 2 of these, you'll kind of see the pattern. They kind of go like this. All right, there's some more formulas we need though. Anybody know one formula we need for sure? What did you say?
I just said y equals mx plus b.
Y equals mx plus b. Well, we're going to use Desmos, so we don't have to do that this time. But yeah, if you were graphing it, you have to put in y equals mx plus b. The ones I said we always got to throw on here. Can't have a negative amount of model airplanes, right? So you got to have 0 or more for both of them, for Model A and Model B. All right. Anything else? Oh, the profit function. Model A earns $12 per unit sold. Model B earns $8 per unit sold. So this is our Z function, our profit function. We'll need that in a minute. All right, let's go graph it. I think I already have this in here from last class. If I can just undo what I did a minute ago, let's see. It did let me. Okay. So you put all those in there, and like one thing when you're doing Desmos, it's going to look like this, and you'll be like, well, that's going to look weird. Well, I got big numbers here, so I need to zoom out. So you can see our edges here of the darkest area where they intersect. Okay. So those are my 4 spots of intersection. I took a screenshot of that, I believe, right there. So those are my area. Like any of these can work. Like it. That's real dark, isn't it? I gotta be right here. I know it's hard to see with the glare, but that is my area right here. I could choose anything in this area. I'd fit all the constraints. I'd stay under my time manufacturing. Like we only get so much time to manufacture than a different company uses or whatever. But one of my maximums is going to be one of these numbers. Okay, one of these edges. So now I take each of those numbers and I'm going to plug them into the objective function that we came up with. So just start plugging them in. 12 times 0 plus 8 times 0. Obviously, if I don't manufacture anything, I'm not going to make any money, so I don't think that's it. 12 times 0 plus 8 times 90. That's 0, so 720. 12 times 60 plus 8 times 40 would be 720 plus 320 would be 1040. And then 12 times 90 plus 8 times 0 would be 1080. So my answer here is actually the 1080. Whoops. It would actually end up being better to only produce Model A airplanes, take all that time of assembly and all that time of packaging, and focus it all on Model A because it's a better profit than doing the Model B. But, maybe our consumers like a little bit of variety, Model A and Model B. We only lose $40, which is only, 0.5% or whatever. So it might be better to do this, but if we want to actually maximize our profit, you would end up actually doing just 90 of A and forget about B completely. Okay? So that problem is